Lesson 10. This is lesson 10 of the A-Level Physics No Frills lesson series. It's me and a whiteboard. And today's lesson is about conservation rules. Now, we've already started looking at conservation rules in the previous lessons. We know that there are certain things that are always the same, certain quantum numbers that do not change with different interactions. We say these quantum numbers are conserved in those situations. So what is conserved in all interactions? Conserved in all interactions. Well, straight off the beginning, we've got charge. Charge is conserved in all interactions. Then we've got things like baryon number. Remember, we met that last time. Baryon number, where quarks have a baryon number of 1/3, antiquarks have a baryon number of -1/3. We also had two different lepton numbers. We had L with a subscript E, the lepton number. I've run out of room at the side of the screen, so let's write that underneath. We had the lepton number, but we also had the muon lepton number, and they were conserved separately, just like that. Now, there are some other things as well, like spin, which I'm not going to include in this, and I'm certainly not going to include energy and mass at the moment, because I want to talk about that in a little bit. It's not quite as simple as I've said, and you'll probably pick that up from what we've said in previous lessons. So these conservation rules, they are used to work out what we can observe and what we cannot observe, what we do see happen and what we do not see happen. And there was a weird one, which was strangeness. Now, strangeness was conserved when creating quarks and antiquarks with the strong interaction. So conserved in actually all interactions except the weak interaction. In all interactions except, is that how you spell except? Feels like it might be right. Except weak. No, that's not how you spell weak. Weak. Except the weak interactions. And there's only one of those, which is strangeness. Actually, there are more. You know, this is not the whole story for real physics. I could add into the conserved in all interactions the tau lepton number for tauons or tau particles, but that's not on your course. I could add into here charm. I could add to here topness. And I could add to here bottomness. Now, what symbol do I use for bottomness? I can't use a B because I've used that for baryon number. But these are also conserved in everything except weak interactions. But they're not on our course. They're not part of our A-level. So that's just an aside to show you that the world of particle physics goes deeper than we have already met. So what we usually say is that strangeness is not conserved with the weak interaction. We call it a decay. The weak interaction's special. Weak interactions are the only ones that can change the type of quark. Are the only interactions that can change the quark type. So what do I mean by that? Well, with a strong interaction, we can create equal amounts of charge and anti-charge, quarks and anti-quarks, should I say. But with the weak interaction, we can actually change the nature of a quark. And it's not just quarks that can change nature. We can change the nature of leptons with the weak interaction as well. So leptons do not interact with the strong nuclear force. So if we ever see an electron and a positron being created, it could be from the electromagnetic force, but it could be from the weak nuclear force. And actually, a very high energy physics, those two forces are indistinguishable, and we merge them into a single force, the electroweak force. And again, that goes beyond A-level physics. So leptons don't interact with a strong nuclear force. You see leptons involved in the interaction, you know it's either electromagnetic or weak. And there are particles that you have not yet met. All sorts of particles that you have not yet met. For example, you've not yet met the lambda particle. Now the lambda particle, and I'm going to put this under more from the zoo, from the particle zoo. There are more particles you have not yet met. So you know about protons, neutrons, electrons, and so on, but you've not met things like the lambda particle, capital lambda. That's what that symbol is. And the capital lambda has a quark composition of up-down strange, but it is not the same thing as a sigma zero. No, in fact, the sigma zero, and I forget which way round it is, I think the sigma zero actually has more mass than a lambda zero, if I've remembered that correctly. In the lambda zero, you've got these three quarks, and the sigma zero also has three quarks that are also up, down, and strange. But what's different is how those quarks are put together. And we'll come into that when we look at quantum physics later. We've also got delta particles. The delta plus is up, up, down, but it is not a proton, which is also up, up, down. And again, it's for the same reason. They've got the same number of quarks, the same types of quarks, but they're put together in a different way. We've got the delta zero, which is up, down, down, but that is not a neutron, which is up, down, down. Same number of quarks, same quarks, but they're put together in a different way, which actually changes the mass of the composite particle. We've also got delta minus. Now that is a down, down, down. And we've got a delta 2 plus. That is an up, up, up. And you can look at the properties of those particles. Now, delta particles don't appear on your specification as you having to memorize them, but they could well come up in an exam in terms of the quark composition and their properties. We need to know that. We've got sigma. We've met sigma plus, which would be your up, up, strange. And we've met sigma zero, which I've already got on this page, so I'm not going to write that. We've also got sigma minus, which is down, down, strange. But what about if there are two strange quarks? If we have two strange quarks, we have our xi particle. And we can have a xi zero, which is a down, is an up, strange, strange. And we could have a xi minus, which is a down, strange, strange. And all these have antiparticles as well. And then we've got our omega particle, which is a strange, strange, strange quark. And that's just up, down, and strange quarks. And we put them together in lots of different ways. We could use an asterisk to indicate an excited state as well. And then we can have the other types of quarks that aren't part of your course. The charm quark, which is just like an up quark, except it's got this property called charm. Just like strangeness, it's another property, another quantum number that is conserved in strong interactions. We've got a higher generation of quarks yet, called the top and bottom, or sometimes called truth and beauty quarks. And they have this property, truthness and beautiness. Actually, we don't call it that. We call it topness and bottomness, which, again, is conserved in strong interactions. We think, but some weird stuff happens with bottom quarks where it appears to break certain symmetries. This is cutting-edge physics, and it's absolutely fascinating. But let's get back to our conservation rules. So we've got more exotic particles in here. And these are all hadrons. I've not included electrons and positrons or muons and anti-muons. You know, there's a lot more here, and I just use the words casually, but you've got to learn this sort of stuff. So let's have a look at an annihilation event between a proton and an antiproton. And let's suppose that that decays into a pion, a pi plus particle, and a negative pion. Well, if we want to check and see if that's possible, we check the conservation rules. These are the charges, and do they work? Well, of course they do, and I can put plus and then negative like that. I'll put brackets around it so mathematically it's a bit more consistent. They do. Right, let's try our baryon number. This is 1 and -1 because it's an anti-baryon. This is 0 because these are mesons, they're not baryons. Is that balanced? Yes, it is. And we can check our electron-lepton number, muon-lepton number. These are rather boring to check, but we could check it. 0 plus 0, 0 plus 0 is equal to 0 plus 0, 0 plus 0. So that observation we can observe, and we do observe it. We do observe that. So we can put down here is observed. And this is how we would lay it out. Now let's try another one. Let's try a proton annihilating an antiproton, and let's see what comes out of this one. Well, let's have a proton come out and a pi minus, like that. Now let's check our conservation rules. Let's get our pen. We have charge. Oh, wrote that in the wrong place. We have charge 1 plus -1, that's equal to 0, is 1 plus -1. Charge appears to work. Now let's try our baryon number. See if baryon number's conserved. 1 plus -1, that's 0. Is that equal to the right-hand side? 1 plus 0. Remember, the pi minus contains a down quark and an up anti-quark. So that doesn't work. It's not a baryon. And that, there's no point in even checking the lepton numbers. It doesn't work. This is not observed. Now, if we just look at that the first one of these, let's look at the first one of these in terms of quarks. What's going on here? We've got an up and a down, plus we've got an up and a down, but these are anti-quarks. So how many ups do I have in total? And how many downs do I have? Well, I've got 1, 2, and I've got 1, plus, well, these are antiparticles, like that. Now that decayed into a pi plus, which is an up anti-down, and a down anti-up. That's the pi 0. I'm looking at number 1 on this top of this list. Is that does that balance? Let's just check it. We've got 1 up quark, and we've got -1 down quark, plus we've got -1 up quark and 1 down quark. So yes, it all balances. The quark numbers balance. We have not created or destroyed quarks, except in equal amounts of quarks and antiquarks. And we have not changed the nature of any quarks. Now, if we look at the second case, still looking at the strong interaction, because this is a anti-proton annihilation. Let's look at the second case in terms of our quarks. What's going on? Up, up, anti-down. And that's going to decay into our proton, which is up, up, down, plus our negative pion, which is a down anti-up. Now, you just got to learn these things. You can actually work them out from the properties. Adding up the charges of the down and the anti-up gives you -1, which is the charge of this meson. So it's just it's a puzzle. It's a satisfying and not altogether tricky puzzle, adding up these charges. So this is 2 plus -2 up quarks. This is 1 plus -1 up quarks, just like we had last time. Does that equal what's going on over here? I should have put a does not equal sign there, shouldn't I? Is there any others that aren't? No, that's fine. Should have put a does not equal sign. So let's have a look at the right-hand side. This is 2 and 1. And this is -1 and 1. Now, clearly, these do not balance. This is not possible at all. The conservation, why wouldn't it undo? The conservation rules forbid that from happening. Okay, fine, and we can look at some other examples of this, but that's how that works. Now, what about interactions that involve the weak nuclear force? Well, let's take an interaction that we know is observed because we've seen it in a previous session, the beta decay. In a beta decay, we call it a decay. The weak nuclear force is involved, and the weak nuclear force is going to change the nature of a quark. So we can say that we have a neutron turning into a proton plus an electron plus an electron antineutrino. So now let's check our conservation rules. And we can check quarks in a second. So we've got charge 0 is equal to 1 plus -1 plus 0. That works. And then we had baryon number is equal to 1 is 1 plus 0 plus 0. So that works. And lepton number, I'm just going to do electron number because there are only leptons involved in this. Remember, matter leptons have a lepton number that's 1, and antimatter leptons have a lepton number that's -1. So that works. Now let's look at it in terms of quarks. Well, in terms of quarks, the neutron is up, down, down. And we're saying that that turns into up, down, up, down, plus the electron antineutrino. So now let's check what's going on with our quarks. And might as well just stick with the black pen. Up quarks, we've got 1 equals 2. Doesn't look like it works. Then down quarks, we've got 2 equals 1. So clearly what's happened here is we have had a down quark turn into an up quark. So this is evidence of the weak interaction. Now, the weak interaction only acts in this way if it is reducing the energy mass, the mass energy of the particles. So we say energy is conserved, but we do have to be a bit careful with this. For example, I'm not going to go the other way on this interaction. I can't get a proton and happen to collide it with an electron antineutrino and turn it into a neutron. It doesn't work that way. And we could have a look at another example. Let's consider the work of a strange quark in taking a sigma particle. Not strange quark. Yeah, strange quark. We've got a sigma particle, and let's say it's a sigma minus. And it's going to decay into a proton. And we'll figure out what's going to come out after it as well. So in terms of quarks, right here, we have got up, down. No, we haven't. We've got down, down, strange. And this is going to turn into up, up, down. So there are two changes there. This perhaps was a bad choice. Let's go like that. Let's go sigma 0. I'm trying to think of a particle interaction that does happen, and there are some interesting problems with that. Sigma 0. Yeah, let's go with a sigma 0. I think we'll be okay with this. So this is up, down, strange, turning into up, up, down. So we can see straight away what's happening is the strange quark is turning into an up quark. That's what's happening. Now we have to conserve charge. If this is a weak interaction, we can have leptons involved. If it's a strong interaction, we can't. But let's have leptons involved. Let's have a muon involved and a muon antineutrino, just like that. Now, if we check our conservation rules, this absolutely can work. We can go charge is 0 equals 1 plus -1 plus 0. We can go baryon number is equal to 1, 1, 0, 0. And we can go lepton number, and we're going to go muon lepton number, 0, 0, 1, -1. So all of those conservation rules work. But we clearly are changing a quark from one type to another. So that is a weak interaction. Now, can I get this to go the other way? Can I get a proton turning into a sigma 0? Can I get an up, up, down turning into an up, down, strange? Oh, I did forget to mention the strange to the down is necessary. Strange to up is necessary because we are using a W boson. You can decay from a strange to a down quark, but it involves the Z0 boson, which lies outside the scope of the A-level course, which is why I had to be careful in choosing what was happening. So here I have my up quark changing into a strange quark. Now, the weak nuclear force doesn't have to conserve the type of quark. It can change it from one type to another. And as long as I add the right particles after it, for example, an anti-muon and a muon neutrino, it looks like the conservation rules are going to be satisfied. Let's just move this around a bit because I don't have a lot of space here on this page. So let's just move, I didn't quite get it all. Let's just move all of this up a bit, give myself a bit more room. And I can move all of this up a bit as well. It's easier to do this, it's easier to do this on a computer, move notes around to make a bit more space. On paper, much more challenging. And I will move this as well. There we are. All this faffing around actually gives you time to make sure you catch up. It's not a bad thing. Oh, and let's... Oh, do you know what? I'm going to move that. Where's the best place for me to move it so I can grab it later? I'm going to move this down to here. Because I want to put number 1 next to number 1. That makes more sense for your notes. Maybe I'll edit this later, maybe I won't. We're looking at number 1, and then we do number 2. Like this. And then number 2. Like this. I think that's going to be a little bit easier for notes revision. There we go. 1, 1, 2, 2, looking at it in terms of particles and in terms of quarks. Good. This will allow me to move all of this up and give me a little bit more room to play with. And all of this back down. Right, I've stopped playing. Let's get on with this. Let's have a look at the conservation rules. So just a reminder before I start moving notes around, we're looking at a situation and whether or not it's possible. Now, charge appears to be conserved. If I look at the charge, this is 1 is equal to 0 plus 1 plus 0. That appears to be conserved. If I look at baryon number, it appears to be conserved. This is 1 equals 1 plus 0 plus 0. It checks out. If I look at lepton number, this is a muon lepton, it appears to be conserved. This is 0 is equal to 0 plus -1 plus 1. So the conservation rules all show that this interaction is possible, but it's never observed. This interaction here is never observed, even though the conservation rules look like it should be possible. So the question is, why is that? And the reason is because the sigma 0 particle has more energy than the proton. Now, it is true that we can collide two particles, destroying mass and creating energy, or should I say destroying energy and creating mass when we collide them. That does happen. We know from annihilation that mass is destroyed and energy is created. So we tend to say energy is conserved, but treat mass as if it's a type of energy. That's important. Energy is conserved, but mass is treated as a type, and I don't like that phrase, so I'll put quotes around it, of energy. Well, okay, that doesn't really answer the problem. Why doesn't this observation happen? And it's because decays go in the direction to reduce that energy, spread it out. Decays work to spread out the energy, to increase the entropy, which you haven't studied yet. Not collect it in one place, not increase the mass. The mass of these particles here is greater than the mass of the proton. But if we go here, the mass of this is greater than the mass of them. Now, I could probably try and put that in my notes. Let's use an orange pen. Let's annotate it. So, mass of the sigma 0 is greater than the sum, and now I can't use a sigma for sum, greater than the mass of the right-hand side. Let's do it like that. Let's say the mass of the left-hand side, like this. Mass of the left-hand side is greater than the mass of the right-hand side. But here, the mass of the left-hand side is less than the mass of the right-hand side. And it's for that reason we see that interaction happen, but we do not see that interaction happen, the second interaction. It doesn't happen for that reason. Yes, mass is not conserved, but energy is conserved, treating mass as if it's energy. But it's more subtle than that. The mass can only decrease, spreading that energy out, taking the energy that's locked away as mass and pushing it into other energy stores like kinetic energy. That's fine, and we can only work in that direction. Now, I know these notes get a little bit cluttered, and that's because that's quite a complicated thing to think about. But there we have it. I haven't done the baryon number checks on these quarks, but I think you get it. I don't think that's too complicated. Just remember the baryon number of a quark is 1/3, and then you can do exactly the same check as we've done here with the other quantum numbers, but with baryon numbers on quark interactions as well. Each time I've used quarks, I haven't bothered, you see. I haven't bothered. Very, very dense page of notes for this lesson. So it might take you a little while to absorb it. And in fact, I might even move some of these things around further, because I think it would be better if I put that somehow underneath, like that. Might just fit. Let's move that down and put that underneath for the same reason. We do get that observation. We don't get the other one. Let's move the X over there. And there we have it. That's the end of lesson 10.